All right, welcome to your personalized deep dive. Today, we're going behind the scenes of the
Us.
Java virtual machine,
Sounds good.
the JVM, right?
Huh.
The unsung hero that makes Java's write once, run anywhere,
Yeah.
magic
More.
possible. Let's start by addressing the elephant in the room. What
Stress.
exactly is the JVM?
So imagine the JVM as a specialized engine for running Java programs
Okay.
when you run your code.
Yeah.
It doesn't go directly to your computer's operating system.
Mm-hmm.
Instead, the JVM acts as an intermediary.
Okay.
It takes your compiled Java code in a format called bytecode and translates it into instructions your operating system can understand.
So it's like a universal translator for Java, allowing it to run on different platforms.
Exactly. This is how Java achieves platform independence. The JVM handles the tricky task of interacting with the underlying operating system. So your code doesn't have to, it just runs smoothly, no matter what system you're on.
That's pretty ingenious. But how does the JVM get your code ready to run? It can't just execute bytecode straight out of the box.
Absolutely not.
Yeah.
There's a crucial step before execution called class loading. Think of it like this.
Okay.
Before the JVM can run any part of your Java code,
Mm-hmm.
it needs to gather all the necessary instructions and data,
Mm-hmm.
which are organized into units called classes.
So it's kind of like setting up a workshop before starting a project.
That's a great analogy. The JVM uses a component called a class loader for this.
Ah.
And you can imagine it as a very efficient librarian.
Okay.
This librarian's job is to locate the right books, which are your classes, from a massive library called the class path.
And the class path is where all my project's code and libraries live.
Exactly. There are actually three main types
Hmm.
of class loaders in Java.
Okay.
First, we have the Bootstrap class loader, which is responsible for loading the most essential Java classes, the core of the language itself.
So it's loading the foundational building blocks of Java.
Precisely. Then we have the extension class loader. This one handles loading classes from extension directories,
Okay.
which provide additional functionality beyond the core Java API.
Hmm.
Think of it like adding specialized tools to our workshop.
So it expands the capabilities of what we can build.
Right. And finally, we have the system application class loader. This one focuses on loading the classes
Okay.
from your application's specific class path, meaning the directories and JAR files that contain your project's unique code.
So that's where the blueprints for my specific project come into play.
Exactly. And here's where it gets really interesting. These class loaders work together in a hierarchy. It's like a chain of command,
Okay.
with the Bootstrap class loader at the top.
Interesting. How does this hierarchy actually work?
Let's say the JVM needs to load a class. The system application class loader first checks if it's parent.
Okay.
The extension class loader has it changed. The extension class loader then checks with its parent, the grandparent Bootstrap class loader.
So each class loader checks with its superior before taking action.
Precisely. This system ensures the most essential classes are always loaded by the Bootstrap class loader, preventing conflicts and ensuring everything runs smoothly. And there's an important security aspect here too.
Oh, tell me more about that.
Well, by always using trusted core classes from the Bootstrap class loader, the JVM protects itself from potentially malicious code, trying to impersonate those core classes.
That's a clever way to maintain the integrity of the system. So the JVM finds the class it needs, but what happens next? Does it just jump into executing the code?
Not quite. There's a three-step process to get a class ready for execution.
Okay.
First is loading, where the class loader locates the class file, essentially a blueprint of your code, and reads its bytecode. Think of it like finding the right blueprint and laying it out on the workbench.
Okay, we found the blueprint. What's the next step?
Next comes linking. This is where the JVM ensures the class fits neatly into its environment. Imagine checking that the blueprint uses standard symbols, the measurements are consistent, and that any reference parts are available.
It sounds like a critical quality control step.
Exactly. The JVM doesn't just blindly trust. Any bytecode it finds, it performs rigorous checks to ensure the code's integrity and compliance with Java's rules. This is crucial for safeguarding the system from potentially harmful or buggy code.
That makes a lot of sense. So what's the final step in this process?
The final step is initialization. This is where things really come to life. The JVM executes the class's static initializers, which essentially sets up its initial state. Think of it like gathering all the necessary tools and materials
Okay.
before starting the actual construction based on our blueprint.
So the class is fully prepped and ready for action at this point.
Exactly. And here's a cool detail. From our source material, this whole class loading process is super efficient. The JVM doesn't load every single class in your project up front. Instead, it uses a lazy loading approach.
Lazy loading. Does that mean it only loads a class when it's absolutely needed?
You got it. Let's say your program has a line of code like new B. This is where you're creating a new instance of a class named B. The JVM wouldn't immediately load class B
Okay.
just because it's mentioned in the code. It waits until it hits that specific instruction, then triggers the class loading process for B.
That's a clever optimization. So the JVM finds and preps the classes. But where does all this code and data actually live while the JVM is working with it?
That's a great question. And it leads us to another key part of the JVM, memory management. The JVM needs space to store
Okay.
all the loaded classes, the objects created during program execution, and other essential data. Think of it like the JVM's workspace.
So the JVM has its own dedicated memory to play around in?
Exactly, and this memory is divided into key areas. One is the method area, a shared space where class-level data, including static variables, is stored. Static variables are associated with the class itself, rather than individual instances.
It's like the master blueprint repository and shared resource pool for the JVM.
A perfect analogy.
Yeah.
Then we have the heap area. This is the primary memory space
Correct.
where objects, instances of classes,
Yeah.
are created and reside during your program's execution.
Mm.
Think of it as the dynamic workspace where all the action happens.
It's where those blueprints come to life and the actual construction takes place.
Precisely. And each thread, which you can imagine as a separate worker on our construction site, gets its own stack area.
Okay.
This stack keeps track of method calls, the actions being performed, and stores local variables, which are temporary pieces of information needed within a specific method.
So each thread has its own private workspace within the JVM's memory.
Exactly. This careful memory management enables the JVM to run your programs efficiently and prevent issues like memory leaks. But loading the code and setting up the memory is only part of the story. We need something to actually execute that code,
Okay.
which is where the execution engine comes in.
Ah, the engine that brings the whole JVM to life. I'm eager to hear more about how that works.
Well, the execution engine is like the brain of the JVM.
Yeah.
It's what takes those bytecode instructions and actually makes them happen. It has several key components that work together.
This is getting really interesting. What are those components?
First, we have the interpreter. Think of it as a diligent reader that goes through the bytecode,
Okay.
line by line, interpreting each instruction and executing the corresponding action.
So it's methodically translating and executing the code, step by step.
That's it. But reading and executing code line by line can be slow, especially for code that gets executed repeatedly. That's where the just-in-time JIT compiler steps in.
Okay, so this is all about speeding things up.
Absolutely. Imagine the JIT compiler as a translator who, after hearing the same phrase repeated multiple times, decides to write down the translation for faster access later. It identifies frequently used code sections and compiles them directly into native machine code, the language your computer's processor understands best.
So instead of interpreting the same code over and over, it provides a shortcut.
Exactly. This compilation process significantly boosts performance, making your Java programs run much faster. But there's another crucial player in the execution engine that we can't forget about, the garbage collector.
The garbage collector, what does that do?
Remember all those objects we talked about being created in the heap area? Well, some of them eventually become obsolete. They're no longer needed by the program.
Ah, so like leftover materials on our construction site?
Precisely. The garbage collector is like an automated cleanup crew. Its job is to identify these unused objects and reclaim the memory they occupy, keeping the JVM's workspace tidy and efficient.
That sounds incredibly important. What would happen without the garbage collector?
Without it, the JVM could quickly run out of memory, leading to crashes or sluggish performance. It's an automatic process that happens in the background, freeing up memory for new objects and preventing those dreaded memory leaks.
Wow, the execution engine is quite the dynamic trio. The interpreter for step-by-step execution, the JIT compiler for performance boosts, and the garbage collector for keeping everything tidy.
You've got it. And all these processes, from class loading to execution, highlight the intricate design of the JVM. It's far more than a simple code runner. It's a sophisticated environment that manages memory, optimizes performance, and ensures the reliability of your Java applications.
It's like a well-oiled machine with all these moving parts working together seamlessly. We've covered so much ground already, from class loading to the execution engine. But it sounds like there's even more to this story, right?
You're right.
Our sources mention other interesting aspects of the JVM, like the Java Native Interface, JNI, and native method libraries.
The JVM is incredibly versatile. We'll dive deeper into those topics next time.
Okay.
But for now, let's take a break.
Welcome back to our deep dive into the fascinating world of the JVM. We've already uncovered so much about how it works, from class loading to memory management and the execution engine.
It's been quite a journey. And in part one, we talked about how the JVM loads and prepares classes, making sure they're safe and ready to run.
Right.
But we didn't get into how it actually finds those classes in the first place.
That's a great point. It's like knowing how a library operates, but not how the librarian knows where to find the books.
Exactly. And that's where the class path comes in. Remember, it's basically a list of locations where the JVM searches for class files.
So it's like a map guiding the JVM to the right shelves in our massive Java library.
Precisely. The class path can include directories on your file system, J8R files, which are like archives of compiled Java code, and even URLs pointing to network locations.
Wow, so the JVM can search in all sorts of places.
That's right. And understanding how the class path works is crucial, especially when you're working on larger projects with multiple dependencies.
Because if the JVM can't find the right class in the class path, our code won't run.
Exactly. You'll likely run into the dreaded class not found exception, a sure sign that the JVM is lost in the library, unable to find the book it needs.
Okay, so how can we make sure the JVM always knows where to look? How do we set up the class path correctly?
There are a few ways to do this. One common approach is to use the JVM command line option. When you run your Java program, this lets you specify the class path directly.
So it's like giving the JVM explicit directions to the right bookshelves.
You got it. You can also set an environment variable called class path,
Hmm.
which provides a system-wide class path that applies to all your Java programs.
Ah, so that's like setting a default library location
Yeah.
for all our Java projects.
Exactly. And in more complex build environments, like those using tools like Maven or Gradle, the class path is often managed automatically for you based on your project's dependencies.
Those build tools sound like pretty smart librarians, automatically gathering all the necessary books for us.
That's a great analogy. They simplify the process and ensure all the required classes are available on the class path, ready for the JVM to find and load.
This makes a lot of sense. The class path acts as a crucial link between the JVM and our code. But once the JVM has loaded a class, what can it actually do with it? What kind of information can it extract?
That's a fantastic question. Once a class is loaded, the JVM has access to a wealth of information about it through something called the class object.
So each loaded class has a corresponding class object that represents it within the JVM.
Precisely. This class object acts as a blueprint or metadata container holding all sorts of details about the class.
What kind of details are we talking about?
Well, it contains the class's fully qualified name, which is like its unique identifier. Think of it like the book's title and author, telling you exactly what you're dealing with.
So it's how the JVM keeps track of all the different classes it has loaded.
Right. The class object also tells you about the class's hierarchy, who its parent is, meaning which class it inherits from. It's like understanding the family tree of our class.
So we can trace its lineage and see what characteristics it inherited from its ancestors.
Precisely. And it goes even deeper. The class object also contains information about the class's members, its variables and methods. It's like knowing the table of contents and the chapters within our book.
That's incredible. So by examining the class object, the JVM can understand the structure, behavior, and relationships of any loaded class.
Exactly. And this ability to introspect classes at runtime is incredibly powerful. It's what allows for things like reflection, where you can dynamically examine and manipulate objects and classes while your program is running.
Reflection. That sounds incredibly useful. But I have to ask, why should I care about the class path and class objects? How does all of this actually benefit me as a Java developer?
That's a great question. And it's important to understand the practical implications
Oh,
of these JVM concepts.
okay.
Firstly, knowing how the class path works is essential for debugging those frustrating class not found exception errors we talked about earlier.
Ah, because if you understand how the JVM searches for classes, you can figure out why it can't find them.
Exactly. You can trace the JVM steps, examine the class path configuration, and identify any missing or misplaced dependencies. It's like being a detective, following the clues, to solve the mystery of the missing class.
I love that analogy. And what about class objects? How do those come in handy in the real world?
Well, class objects unlock a world of dynamic possibilities in Java. They're the key to reflection, which lets you write code that can examine and interact with objects and classes in a very flexible way.
So instead of hard coding everything, we can write code that adapts to different classes and objects on the fly.
Precisely. Reflection is used in many powerful Java frameworks and libraries, enabling them to work with a wide range of classes, without knowing their specific details beforehand.
That's amazing. So understanding the class path and class objects gives us both debugging superpowers and the ability to write more dynamic and flexible Java code. It's like leveling up our Java skills.
You got it. These JVM concepts are fundamental to understanding how Java works under the hood, and that knowledge makes you a more effective and confident developer.
I'm starting to see the bigger picture here. The JVM isn't just some black box that runs our code. It's a sophisticated system with its own rules and mechanisms that we can leverage to write better, more efficient Java code.
That's exactly the point.
Yeah.
The more you understand about the JVM, the more you can appreciate the elegance and power of the Java platform. A beautiful dance between your code and this amazing virtual machine.
This deep dive has been an eye-opening experience. We've explored the inner workings of the JVM, from class loading to memory management and the execution engine. And now we've uncovered the secrets of the class path and class objects. But can we go even deeper? Is there a way to see what's happening in real time as our code is running?
You're thinking like a true deep diver, and the answer is yes. There are powerful tools that let you monitor and analyze the JVM's behavior as your code executes. They provide insights into memory usage, garbage collection, thread behavior, and even the performance of individual methods.
That sounds incredibly useful. What are some of these tools, and how can they help us write better Java code?
One popular tool is called JConsole. It comes bundled with the Java Development Kit, KDK, and provides a graphical interface for monitoring various aspects of the JVM. You can use JConsole to track memory usage, see how often garbage collection is happening, identify potential memory leaks, and even monitor the activity of individual threads.
So it's like having a dashboard for the JVM, giving us real-time insights into its performance.
Exactly. Another powerful tool is Visual VM. It's also included with the JDK and offers even more advanced profiling and analysis capabilities. With Visual VM, you can take snapshots of the JVM state at different points in time, allowing you to compare memory usage and object creation patterns. You can also use it to trace the execution of specific methods, identifying performance bottlenecks and areas for optimization.
These tools sound like game changers for Java developers. By understanding how our code affects the JVM's behavior, we can make more informed decisions about how to write efficient and performant applications.
Absolutely. These tools can be invaluable for identifying and resolving performance issues, memory leaks, and other problems that can pop up in complex Java applications. They offer a window into the JVM's inner workings, letting you optimize your code and ensure your applications run smoothly and efficiently.
This has been an incredible journey. We've gone from the basics of class loading and execution to the intricacies of the class path and the power of class objects. And now we've even explored tools that let us monitor and analyze the JVM in real time. I feel like I've gained a whole new level of understanding and appreciation for Java.
Me too. It's been a pleasure sharing this deep dive with you.
Yeah.
But we're not finished yet. There's still more to explore.
Welcome back to the final part of our deep dive into the Java virtual machine. We've explored so much already, from class loading and memory management to the execution engine class path, and even those powerful tools for real-time monitoring.
It's been quite an adventure through the inner workings of the JVM.
It really has. But before we wrap up, I'd love to pull back and look at the bigger picture. Why does all this matter to us as Java developers? What's the practical value of understanding these internal mechanisms?
That's a great question. It's easy to get lost in the technical details. But ultimately, understanding the JVM empowers you to write better code, more efficient, more robust, and less prone to those head-scratching bugs.
So it's not just theoretical knowledge, it directly translates into practical coding skills.
Absolutely. For example, knowing how the garbage collector works helps you write code that minimizes the creation of unnecessary objects. That means better performance and fewer memory-related issues.
It's like being mindful of our workspace and keeping it tidy, so the JVM's cleanup crew has an easier job.
Exactly. Similarly, understanding the JIT compiler can help you structure your code in ways that are more likely to be optimized, resulting in faster execution times.
So we can write code that's more JIT friendly, if you will. I like that.
Precisely. And as we discussed earlier, knowing about the class path and how classes are loaded is crucial for debugging those frustrating class not found exception errors and managing dependencies in larger projects.
Right. It's like having a mental map of that massive Java library, so we can navigate it with ease and find what we need.
Exactly. And let's not forget about the power of tools like JConsole and Visual VM that give us that X-ray vision into our code, letting us see how it's interacting with the JVM in real time. We can spot performance bottlenecks, memory leaks, and other issues that might otherwise be hidden.
That's incredibly valuable. It feels like we've gone from fumbling in the dark to having a powerful spotlight to illuminate the inner workings of our applications.
That's a great way to put it. By understanding the JVM and using the right tools, you can write Java code that is not only functionally correct, but also highly optimized and reliable.
This deep dive has been a real eye-opener. It's amazing to see how much complexity is hidden beneath the seemingly simple act of running a Java program.
I agree. The JVM is a marvel of engineering, and the more you understand about it, the more you can appreciate the elegance and power of the Java platform. It truly is a testament to the ingenuity of its creators.
And the journey doesn't end here, right? There's always more to learn and explore in the world of Java and the JVM.
Absolutely. The Java landscape is constantly evolving, with new features and enhancements emerging all the time. So never stop exploring, never stop learning, and never stop pushing the boundaries of what's possible with this amazing language.
Well said. Thank you so much for guiding us on this incredible journey through the Java virtual machine. I feel like I've gained a whole new level of understanding and appreciation for Java, and I can't wait to put this knowledge into practice.
It's been my pleasure. And to all our listeners out there, thank you for joining us on this deep dive. We hope you've enjoyed exploring the inner workings of the JVM with us, and that you'll walk away with valuable insights to help you write even better Java code. Happy coding, everyone.